right, so remind me about some kinematic relationships here. I forgot. What's the definition of velocity? Derivative of position. Okay. Right? Okay, good. So that's velocity. What's acceleration?
Derivative of velocity. Derivative of velocity.
Okay, so derivative of velocity. So how would that be related to the second derivative of position? Okay. Okay, that's interesting. Okay, so
Doesn't even know what acceleration is.
Okay. All right. So we know. Tell me about the acceleration of gravity at the Earth's surface. Okay. So it's constant, roughly, right?
Yes.
So let's just say, let's take any situation where acceleration is constant, how about, right? So we'll say acceleration is constant, and we're just gonna call it A, okay? So let's see, what is V then, in terms of, let's see here, let's see if we could do something with this maybe. So we'd have the equation dV dt equals A, where A is a constant, right? Well, that's a differential equation. So let's solve that. How are we going to solve that?
Multiply by dt.
Multiply by dt. Okay, so we'll go through the full meal deal here. We'll now what?
The sign.
Times x minus.
So we'll integrate,
Yeah.
right? Or anti-differentiate, I guess you guys are calling it now. That's what all you kids are calling it these days, anti-differentiation. That's fine. So then we get V. What's going on there?
Oh.
So V of t, function of time, is what then? What's the,
A to the sec.
A is a constant, right?
Yeah.
So it'd be AX.
AT,
AT.
okay?
Yeah.
Plus C.
Yes.
Okay. Okay, good. Well, what about that C? How can we deal with that? Just leave it? I have an idea. Why don't we do, what if we said, okay, let's let t equals 0. If I let t equals 0, what does this equation become? V of 0. What do we call that in physics? The velocity at time 0. What do we call it? Initial velocity. Yeah, so we'd end up with initial velocity equals a times 0, which is 0, plus c. Aha, so c represents the initial velocity. Oh, interesting. Okay, so then that gives us an important kinematics equation. So that tells us that v equals at plus v naught.
Oh, hell, we just solved like, what?
Interesting. Interesting. Okay.
So those good for nothing physics people just take things for granted.
I know. Okay, well, we can go further than that. So now we could do another differential equation because you guys told me that ds dt equals v, right? Okay, so we can go one step further with this. We could say ds dt equals v, which is that stuff, right? So that's another differential equation. We can solve that, right? On this one, let's go ahead and take the shortcut. We know that if this is the derivative, then that must be the integrand, right? So we could skip a step and say the differential equation we're going to get is s of t equals the antiderivative of at plus v naught dt, right? Everybody okay with that? Is that good? Give me I need a 1 to 5 on this. You gotta vote.
Wait,
1 to 5. 5 means that is perfectly clear, Mr. Roy. 1 means don't have any clue.
2 to 3.
Okay, then let's,
Okay, or
all we did was skip those steps, right? So really all we needed to do, everybody with me?
Yeah.
Okay, so I would just multiply each side by dt and then integrate, okay? All right, well, let's solve this differential equation. That's an easy one to solve. So S of t equals what? We just anti-differentiate term by term. So what's going to be the antiderivative of a t dt?
T to the A.
A is a constant,
Oh.
right?
So. it
T
would be
times
t
A minus.
squared.
No.
So it's the a, we could even put that a out in front of that integral, right? But what's the antiderivative of t dt?
T squared
T squared over,
over.
T minus 1.
Nope.
well, let's go back
T squared over 2.
over 2. Because that's our, remember, if you were here yesterday, if you chose to attend, even if you didn't, I'll give you one.
What are you trying to say?
Yeah. There was a present.
My mom told me I couldn't go to school.
No, that's,
Oh.
my daughter's homesick today too. So, here you go. Here are the standard forms. And yesterday,
Oh,
What, Ian?
I showed everybody how to get those, right? We're just gonna take the derivative rules that we had, and we're just gonna turn each of those into integration rules. Well, there's an important one on there, the power rule, right? So, rule number 4. So we know that the antiderivative, let's just write that one down real quick. The the integral. So what do we got here? We got the integral of x to the n dx is what?
X to the n over n.
X to the n plus 1 over n plus 1 plus
Say geniuses over here.
right? So then these are t's instead of x's, but same deal. So the antiderivative of t to the 1 dt is t to the 1 plus 1 over 1 plus 1, right?
Yeah.
So it's going to give us a times t squared over 2. What's the antiderivative of v naught dt? V naught's a constant, right?
V not t. Vought. It's vought.
Plus some
Oh my God.
constant, call it C2.
Oh my god, that's kinematics number 3.
Yeah.
Oh, it could be, right?
That's honestly how I got the 2. 'Cause I
So once
didn't
again-
remember the rule from yesterday.
If we let t equals 0, what does this become? S of 0 is S naught, not snot, it's S naught, right? So we get S naught equals 0 plus 0 plus C sub 2. So C sub 2 is initial position, right? Okay. So then this just becomes S of t equals 1/2 at squared plus v naught t plus S naught. And if we choose to, we could say
Oh, hell.
we could say that final position minus initial position, so S minus S naught,
Change the displacement.
Oh,
right, which is just displacement. So what do you know? Okay? How about that? So all we did,
It just shows the physics.
all we had to
We
do
use it
was
for
just,
physics,
was just make the assumption that acceleration is constant, and 2 simple differential equations gave us 2 of the most important kinematics equations we've used all year,
We
right?
should do that in physics because like
I think I'm not gonna do that.
why?
Yeah.
The looks on their faces yesterday were priceless. They
Yeah.
weren't even really difficult things, but they freaked out when they heard calculus.
Yeah, that's,
I was like,
honestly,
oh, shit.
just the word calculus is scary.
just causes
Yes.
panic.
Yeah, we
Causes
should.
panic in the masses, yes. Okay, so,
Hysteria.
so that's,
Good day at work, guys. Let's go.
Lunchtime.
so then I think I'm prepared to let you guys have one day to catch your breath on this stuff, and then tomorrow we're launching into new stuff.
I thought
Okay.
that was the news. No, the test.
I'm gonna be gone tomorrow on Friday, so what am I missing?
You're gonna miss,
Probably a lot of important things.
you're gonna miss a lot of stuff, but I'll tape it.
Okay.
Yep.
I'll just be out tomorrow.
Always prove it.